Good morning all. The second part of the fourth module of Geotechnical Engineering 1 is about compaction of soil. Now when we talk about engineering properties of soil, we have three in number: shear strength, permeability, and compressibility. In compressibility, we have dealt with the consolidation of soil in the first part, and now we have the compaction of soil. Consolidation and compaction are parts of the compressibility property of soil, but are quite different from its behavior. When you go out to the field for, let's say, the construction of an embankment for road construction, you'll have to place the soil in a particular density, for which you'll use rollers or compactors to ensure that the field density is the one that you are intended. Now you can either use rollers like this, or you can use heavy falls like this, which is about dynamic compaction of soil, dropping a big weight onto the soil, and it is a dynamic method of compaction. Now compaction nonetheless is about reduction in the volume of voids, quite similar to the consolidation but different in nature. In consolidation, it was about expulsion of water. Here it is about expulsion of air. So compaction is nothing but reduction in volume of voids and thereby increasing in density by expulsion of air and not water. So the compaction is done to improve the engineering properties of soil, including the shear strength and reducing the permeability, etc. It is fundamentally the pressing of soil particles to each other by mechanical process, and it involves expulsion of air. The compaction results in decrease in void ratio and hence an increase in soil density. To compare the compaction and consolidation, three-phase system diagram is shown here. In consolidation, which is the one that we were discussing in the previous videos, you had a saturated soil sample. You have solids here and water here. During consolidation, what happens is that the volume, the total volume, reduces by reduction in the volume of water, which means water got expelled out. And when you talk about compaction, you don't have fully saturated soil, instead you have partially saturated soil. You have solid, you have water, and you have air voids. In compaction, the reduction in volume is not due to the reduction in water, but due to the expulsion of air. So if you compare these two three-phase system diagrams, you can understand the difference. Here, the quantity of water remains almost the same, but the volume of air got reduced, which means air got expelled out. Whereas in consolidation, you didn't have air in the first place, and if there's any reduction in volume, it's entirely due to the expulsion of water. So the differences are marked here. Compaction is a sudden process of volume reduction, whereas consolidation is a gradual process of volume reduction. Compaction is dynamic loading, where consolidation is static loading. Compaction happens in partially saturated soil, whereas consolidation is something that is in fully saturated soil. Compaction is by air removal, whereas in consolidation it is a removal of water. Compaction is usually an artificial process, whereas consolidation is usually a natural process. To move further about the properties of soil during compaction, we'll first discuss the PROCTOR compaction test in the laboratory. Now, PROCTOR compaction test is carried out in the laboratory to decide on what amount of water and what degree of compaction is required in the field to attain a target density. This test provides the relation between the water content and the dry density. So fundamentally, if you are out in the field to construct, let's take the same example of to construct a road embankment, you'll be given with truckloads of soil, and your intention as an engineer will be to provide the maximum density of soil for which there will be an optimum water content, which is mass of water by mass of solids, to be supplied or sprinkled on the soil to ensure that you attain the maximum density or the maximum dry density to be specific. So in the field you'll be given with an optimum moisture content which you arrive based on the Proctor compaction test that you conduct in the laboratory, for which you have a standard Proctor mold 10 centimeter or 100 millimeter in inner diameter and 12.4 or 12.7 centimeters in height, the inner height. This is a mold, and above which there will be a collar which protects this mold from the dynamic action of this hammer. This is again a standard hammer, and the process is described as below. The standard Proctor test, you have a mold 12.7 centimeter height and 100 millimeter diameter with a detachable plate and a collar. A hammer, a standard one, with 2.6 kilogram and a free drop of 31 centimeter is used to compact the soil. Now the soil is placed in layers and compacted using this standard hammer. The process is by filling the soil in 3 layers and each layer given 25 blows from the hammer. So you have a hammer 2.6 kilograms falling from 31 centimeter height, and it blows onto the soil 25 blows for 1 layer, and you have 3 layers to make up to the 12.7 centimeter height. Procedure in detail is here. Take about 3 kilograms of soil. The initial water content is determined by oven drying method, and then water is added to make the initial water content about 4% to start with. The soil is thoroughly mixed, and the mass of the empty mold is taken. Let's mark it as M1. The soil is then filled in the mold in layers and by blows as described previously. Extra soil that comes above the mold is trimmed off using a knife or a spatula, and the assembly is weighed. Let the weight be M2. Now subtracting M1 from M2, you will get the mass of the wet soil in the mold, from which you can calculate the bulk density of the soil, because you have the weight or the mass, and then you have the standard volume of the mold, from which you will get the bulk density. A small sample of soil is taken from the mold and it's kept for determination of actual water content. The initial water content was an approximate assumption, whereas when you take a sample of soil from the mold and then when you keep it in the oven, you can actually get the precise water content the next day, based on which you can calculate the dry density of the soil. You have bulk density here, you have the water content here, so from which you'll get the dry density or the dry unit weight. The soil is then removed from the mold, taken out, remolded and mixed with the next increment of water, and the test is repeated. So to start with, you had 4% and you carried out the test, found out the bulk density, found out the dry density. Take the soil out, add the next increment, let's say 2% extra, so that makes 6%. Carry out the test, you'll get one other set of dry density. Then go for the third round, let's say 8%, you'll get another set of dry density. Likewise, this test is repeated. Now, before going into the observations from the test, we have a few combinations of the mold, the rammer, the number of blows, etc. So the choice of test, number 1, modified Proctor test. When you talk about modified Proctor test, the mold is the same, the standard mold, but you have a hammer which is 4.8 kilogram and a free drop of 45 centimeter. Earlier it was 2.6 and 30 centimeters, now it's 4.8 and 45 centimeters. The soil is filled in 5 layers and each layer is given 25 blows, the same. If the percentage of soil retained on 4.75 millimeter sieve is greater than 20%, you use a larger mold. But when you use a larger mold, 56 blows are given to each layer. And if the percentage of soil retained on 4.75 mm sieve is less than 20%, you use the same standard mold, not the larger mold. And when you use the standard mold, you stick on to 25 blows. So a larger mold is associated with a higher number of blows, and a standard mold is associated with a lower number of blows. Now, another combination is about the field condition. If heavy compaction is implemented in the field, you use a big hammer, and when you use a big hammer, you fill the soil in 5 layers. And in the soil, in the field condition, if it's light compaction in the field, you use a standard hammer, and when you use a standard hammer, the soil is filled in 3 layers. So in short, standard hammer is associated with 3 layers and big hammer is associated with 5 layers. Larger mold is associated with 56 blows, standard mold is associated with 25 blows. And the choice of the hammer depends on the field compaction, whether it's heavy or light. Now this was about the choice of the test. Coming to the observation from the compaction test, you have what we call as a compaction curve. You plot the water content in the x-axis and the dry density gram per cc in the y-axis, and what you get looks like this. You have somewhat similar to a bell curve, and as the water content increases, the dry density increases only up to a certain point and then starts to decrease. So that particular point corresponding to the peak value is the maximum dry density, and the water content is the optimum moisture content or the optimum water content. So you draw a curve with water content in x-axis and dry density in y-axis, which is called as a compaction curve, and it's typically a bell-shaped curve. And as water content increases, the dry density increases, reaches a peak point and then starts decreasing. The density corresponding to the peak is the maximum dry density MDD, and the water content corresponding to that value is the optimum moisture content OMC. These two terms are quite important, OMC and MDD. At any water content less than the OMC, to the left side of this dotted line, if the water content is less than OMC, the soil is stiff and hence the void spaces are filled with air. Hence the dry density is obviously less. But any water content to the right side of OMC, water starts to occupy the space that might have been occupied by the soil solids. So this decreases the density. So that is the reason why you have a shape that goes upward, reaches the MDD and starts to go downward. So this is a typical nature of a compaction curve. Zero air voids line. To understand the concept of zero air voids line, let's first take this same graph. You have the compaction curve here, which is the one that you get from the laboratory when you plot the water content in the x and the dry density in the y. So this looks like a bell shape with the maximum point on the y-axis being the maximum dry density and the peak point on the x-axis that corresponds to OMC or optimum moisture content. But it's a fact that compaction cannot remove all the air voids. Even if we use a maximum compaction level and a maximum possible number of layers and ensure accurate compaction, you cannot actually obtain 100% saturation, or compaction in short cannot remove every air void that is present. Hence the soil will never attain fully saturated state. But they can be a theoretical line indicating a case of maximum dry density with air voids equal to 0. That theoretical line is called the zero air voids line. It's also called as a 100% saturation line, and it is somewhere here. So obviously the laboratory test result falls well below the zero air voids line. The expression rho d is here, g by 1 plus c into rho w. This is the same equation that we are familiar with in the first module, three-phase system diagrams. G plus sc by 1 plus c into rho w. When you have s equal to 0 for dry case, you have rho d equal to g by 1 plus c into rho w. But I can replace E as wg by s with the basic relation that we are familiar with. G by 1 plus E is replaced by wg by s. Again, theoretically, in this expression, if I can put s is equal to 1, rho d becomes g by 1 plus wg into rho w, because it's a concept where you don't have any air voids at all, and hence the soil is completely saturated. So I can have g by 1 plus wg rho w, and also it can rather be represented as 1 minus Na by 1 plus wg into g rho w, where Na is the percentage air voids. Compaction control in the field. In the field, for example, when you are constructing a road embankment, it is essential to control and check the water content and the dry density to ensure quality control. So a specific amount of compaction with the OMC is to be ensured to attain target density. Now, to check the target density, methods like core cutter and sand replacement method or even nuclear methods may be adopted. But to check the water content, oven drying method may be used. But the problem with oven drying method is that it will take 24 hours to give you the result, and hence the contractor may not have the luxury of time, and it's not advisable for the field condition. In that cases, a PROCTOR needle method is adopted, and it's used to check the in situ moisture content or the water content in the field. So PROCTOR needle method looks like this, and it's used to check the moisture or the water content in the field. A photograph taken from the internet is shown here, and the schematic is shown here. You have a loading plunger, you have a needle shank, and below which you have the needle point of varying diameters, and you have a sliding ring here and few graduations which indicates the depth to which the needle has penetrated, and you have a handle here as well. Now, as you see from the picture, it has a sliding ring, a stem, a needle shank, and a needle point with a handle attached. The sliding ring on the stem reads the maximum penetration resistance in newtons, and the needle shank indicates depth of penetration. A needle point of suitable area or diameter is chosen based on the soil type, whether it's sand, whether it's clay, etc. You can choose the needle point type. And after compaction of the embankment or the site in the field, the needle is forced 7.5 centimeters into the ground. As you can see from this picture, this is a process of jacking it down. The maximum force required to penetrate is obtained, and the penetration resistance is computed per unit area. And you have a calibration chart already available along with the PROCTOR needle, which you can use to estimate the water content. So the water content is in the x-axis, the dry density is in the y-axis, and you have a secondary y-axis where the penetration resistance is marked. So once you know the penetration resistance, you can get the water content using the calibration chart. So fundamentally, you are trying to penetrate this needle into the ground for 7.5 centimeters, and what you get from the field is the penetration resistance, which is correlated to the water content. So you can find the approximate water content in the field within a few minutes, rather than going for the oven drying method, which will consume 24 hours.